All right. I may kind of put in a few words that aren't necessarily in the chapter there, but on the first page there, they talk about nature's direction, which is always an interesting conversation when you use the term direction to talk about heat and thermodynamics. Because I want to start this lecture with a reminder of something that we did discuss on the first week. And that, well, I believe we did, should have. That's the difference between a scalar quantity and a vector quantity. And I believe that two people in class uh, answered and uh, told the class what that distinction was. Let's revisit that a minute. Does anyone remember what the difference between a scalar and a vector is? Scalar quantity versus a vector quantity. And can you give me a couple of examples? Anyone? Stephanie, are you there? There's a difference between a scalar and a vector. Awesome. You're absolutely correct. Can you give me an example of maybe one example of both in terms of physical quantity? So what you said is that a scalar quantity just has magnitude, and a vector quantity has both magnitude and direction. Nailed it. You're right on the head. That would be 100%. Nailed it again. Well done. Yes, time is a scalar quantity, although we do kind of tend to have some kind of direction. In fact, that's interesting. It's not really a direction, but we do say that in popular terms, right? We when we physically write time, we don't put it, we don't represent it as a vector quantity. It's just a scalar. But in our kind of everyday life, we kind of think of past, present, and future, which implies it's not really a direction, but it's some kind of movement that we think about. And it's interesting. I bring that up because that sensibility is actually associated with the first quantity that they actually talk about, but I don't think they name. I don't see it here. But when they're talking about nature's direction, that's what they mean. It's not really a direction because time is not a scalar quantity. But when you look at physical systems and you look at what happens to those systems over time, there's a certain direction, and I'm using that with carefully because it's not really a direction, but that we kind of, when we look at the energy of systems, they seem to have a behavior that's only in a particular direction. I'll tell you what I mean in a second. But first, just quickly review. So scalar quantity is just magnitude. And examples are time, energy, also a scalar. Um, yeah, mass, and there's some other more advanced quantities. I'm not going to write those down. I thought about it, but one particularly associated with heat and thermodynamics is one of the things that I studied as my PhD, which is specific heat. In fact, my PhD sitting right up there. Specific heat, which actually Einstein said that if you were on a desert island somewhere and you could only, or a desert lab, I don't know, just making that up, but you could only make one measurement. You had some new alien material that fell out of the sky or something. I don't know. And you could only make one physical measurement of all the kinds of measurements that you could make. You know, electrical properties, resistance, resistivity, uh, whatever. Measure its mass. Whatever you could measure. But you could only do one. The one quantity that you probably should measure is specific heat. Uh, the specific heat of the quantity, and that is a scalar quantity. And the specific heat, it essentially tells you the amount of heat energy that an object can take. I should probably write that as well. So I'll put that down. Specific heat. I don't think they have you doing much with that in this chapter, but it is nice to at least talk about specific. And basically, it's a quantity that, like if you take steel and wood and you have them at the same temperature, and then you put them in some sort of heating device, basically the same oven, and you put them in right next to one another so there's consistent heat throughout the oven, and you keep them in there for the same amount of time. When you take them out, they will not have the same temperature, even though they had the same temperature when you put them in the oven. And the reason is because the way the molecules and the atoms are put together, there's all kinds of energy structures and things within the material that is on the atomic and molecular level that you can't see. And materials are very different. That's actually what gives them their properties, the various properties that they have, how they feel, how they behave in certain environments. It's really how the atoms are put together and the things that the states that they make within the material. Anyway, that collective essentially is what I'm saying why Einstein says you can measure it, because is you should measure it, because if you can get an accurate measurement of that specific heat, you can manipulate the data to determine certain very basic things about the material, how it's even chemical properties, physical, electrical, all kinds of properties about the material. It takes a lot of mathematics to extract that information, but it's in there because all of that contributes to why the two materials take heat in differently. Um, but as you might imagine, it takes some effort to make an accurate specific heat measurement, but it's some really good physics. So that's why he said that. Wood would absorb the heat less. Yeah, it would actually. Yeah, that's great intuition. It would absorb the heat less. That's right. Is that right? Actually, that's a good question. I hadn't thought about it. Caught me on this. I have to look it up. I think my guess is that. Ooh, that's a great question. Ooh, okay. It's a complicated question. Now that I'm actually thinking about it, I believe that the heat would be hot, the wood would be hotter. However, and this is one of the things about specific heat, it would be hotter because even though steel can ultimately take more heat than wood, the wood takes the heat in faster. So if you put them in at the same temperature, and it also depends on what initial temperature they're at. Yeah, it's specific heat is pretty. It's one of the more complex uh, quantities you can make. But you know how they say Some people, you might have heard this before because this is related, that hot water or cold water, yeah, this is a, yeah, cold. Have you ever heard the idea that cold water can heat up faster than hot water? Has anyone ever heard that before? No, you've never heard that. Or, well, uh, maybe people don't say that anymore, but they used to when I was a kid. What is, you've heard that. Tamika, you've heard that. Yeah. Okay. That this is the same thing that I'm trying to talk about between the wood and the steel. It's the same reason. So I think it's probably a little bit easier to talk about it with water. So most things in, oh, well, we initially got into such a complex conversation, but it's worth having real quick. And none of this is going to be in your book, I don't think, because this is a little bit more advanced. But there's something that happens, and this is a universal thing, meaning that it's not just with specific heat. It happens with a lot of things in nature we see. There's a pattern uh, by which material activates, and there's an overall pattern, and it's called an S curve. In fact, if any of you have ever gotten involved with any of the network marketing type of things, and some people call them pyramids, which there actually are legitimate business models, but like where it's been basically started from Avon back in the 50s to McDonald's, but now people do it a lot. They have individual businesses and they get you and try to get you in. You go, right, it could be selling whatever, telephones. If you used to do that back in the 80s when cell phones got popular, but you can sell anything with it. But it's a business model where you have some product and you're trying to get people to buy it, but you actually try to get people to be in a business selling that because it actually generates more money. And then they're kind of under you in this, you know, pattern the way they put the business together. And those people go out and get more people in the business. So it's not just that you're selling the product, you're also selling the business. And that can get really saturated in a particular area. It turns out that if you were to graph the business growth versus time for a particular business, it also has the same pattern of the curve as specific heat, for example. And that's something that I call, in the first, I think the first week, I told you there's four themes that I kind of go back to when I'm in my teaching philosophy. And that's, or I think I told you that. It's perspective, specificity, symmetry, and technique. So this is one area what I mean by symmetry. I'm not just talking about geometrical symmetry. I'm talking about certain physical phenomena that seem to repeat themselves even in things throughout our universe and nature that aren't related. Like you wouldn't necessarily think of a network business model to have anything to do with the amount of heat, or how water molecules absorb heat as you're heating it up on the stove. Well, this is one way, something that they do have in common. It's the way that they grow, the way that if I plot the way the business model grows over time and the way heat goes into, the temperature raises, however you measure it, heat, specific heat, or just literally measuring the temperature over time, they follow the same kind of pattern. And that's in general called an S curve. Sorry, I think I took all my markers, my colored markers in school. So this is going to be and it looks something like this. And it's called an S curve because it kind of looks like an S. And there's certain limits that some systems can have. In the case of the network marketing, this might be population versus time. So the population in a particular town or area, because you only have so many people that could possibly be in the business. So at some point, that area would become saturated, and there's no more people, right? And so this would represent that limit, right? And so this is time, and this is say population in the community. So at some point, you're going to reach the saturation. So this curve is telling you how many people per unit time you can get. So right down here at the bottom, there's a lot of kind of qualitative things that I like to talk about when I draw an S curve and talk qualitatively about it. So Now, the slope, I know you know maybe what slope is from mathematics. Slope is rise over run. And the way that you can really quickly determine what a slope is by taking a tangent curve at any point in the path to a tangent to that curve and looking at the steepness of that curve. So, for example, right here, and again, I apologize for not having it colored. Oh, yeah, I believe it somewhere. Let's do this. So, if I drew a tangent down here, the thing is not really slanted very well, right? It's like almost horizontal. So that would be so if I did the rise over the run of this thing, that tells me the slope. But I don't even have to get mathematical. I can just look at it. If I'm calling this flat and 90 degrees the steepest it can be, then anywhere in between that is the slope. It's the steepness of it. Like if I think of it as a hill and I have to go up, this is much steeper than this. So when I look at this guy, well, that's almost flat. It's not very steep. But if I look at someplace else, like right here, and this is the ideal point because this is the steepest it's going to get is about well, it's not necessarily 45 degrees, but it's just whatever it is. Okay, so it's very steep in there, but then when I get up here, it starts to flatten out again, like somewhere here. And then, of course, over here, basically it doesn't really get flat until infinity. Mathematically, is theoretical limit. But generally speaking, the measurable difference in the change happens, much sooner than that, and that depends on certain properties and quantities you can define by extracting it from the specific heat. There's certain variables that will tell you when you're like 60% of the maximum being infinity, but that's going to happen. It might happen in 2 days, so which means that in 12 days, if this is population, depending on what the relative rate is, the measurable difference of how it's changing up here is very small. So this curve, this blue curve that I wrote at different places, what you can think about is that it's the rate of change of that quantity. So in this case of if this is a network marketing business, then this would be the amount of people in the population that in a particular area, marketing, that they're able to get in the business. It's how fast, and it shows how fast the business is growing. But I could very easily change this to specific heat. And so it's going to measure the amount of heat energy, like for water on a stove. So it's going to measure the amount of heat energy that water takes off. Now, let's look at different regions. You've also heard the term that it's harder to start something than to get it going. That's another symmetry that we see all throughout physics, and we're seeing it here because this low slope or minimal slope, it's saying that if I compare the rate at which, in this case, the population is changing, the business is growing, that's another way to say it, as opposed to right here in the middle, clearly it's much slower. So it's harder to get people involved. Wherever you got to go get the thing started. Same thing with water. Like if I'm heating up the water, basically it's harder for the molecules to absorb the heat energy than it is at some time later in the heating process. For example, here where it shows the slope is very steep. And that actually has to do with several of the topics they talk about in the first several sections, not just the first section there, but in fact, we've kind of jumped past that first section. I'm gonna have to go back and talk about that a little bit. But I like to kind of follow based on the vibe of the class. My lectures kind of sometimes they flow a little bit about like that based on the response I'm getting. And so that's why I wanted to jump into this really quickly, is because of the response that someone made a few minutes ago. Anyway, um, the rate of change is much higher here in the middle of this curve because the slope of a tangent at any point is the steepest. So at some point, and if you look at the slope, this is kind of a pattern that happens to the slope. Starts off very slow, very small, then it increases almost linearly there in the middle, and then as you go up, it starts to decrease again. That's what creates the S curve. It's the pattern at which the slope is changing throughout time for the material. And again, as I said, this is a pattern that happens with all kinds of things in nature that are seemingly completely unrelated, like a visiting network uh, uh, network marketing business model as compared to water heating up on the stove. Now, why does cold water heat faster than hot water? Is because if I change this to water, then what we see down here is that the slope, if this is water and this is specific heat over here, see again, I don't have to change anything about the curve because it's a general curve, so it's still going to fit. That's the symmetry I'm talking about. So specific heat, and just very quickly, specific heat then is just the amount of heat that heat energy that an object can take in. Then what we see is that when the water, like this is lower temperature, and this would be temperature, not time. Down here at lower temperatures where it's colder, the slope is flatter, right? So it's hard, and we'll talk about why that is, and your book does too. Although I don't think they talk about it in the context of specific heat, but whatever. Uh, I'll make that gap. So it's harder to get the heat in, but then as you go up, it's easier to get, the heat is going in faster. So there's more heat per unit time, or I could do this in temperature and time, but in temperature, more heat per unit temperature is getting in, and then as you go, to the top of the S curve and the temperature is raising, then that diminishes. So the point is that if you put cold water in this, cold water might be starting down here somewhere, but hot water clearly is going to be starting somewhere, here. So it's not that ultimately, uh, wait, do I have that right? Yeah. Actually, hot water might be over here someplace where it's already starting to saturate. Like maybe hot water starts here. So it's not that, if the water is hot, it's going to reach boiling faster than the colder water. Like that's not right. But if you look at, actually, I was right initially. I should go in here somewhere because it's starting. It's already boiling when it gets up there, pretty much. And I know I haven't made this quantified this graph. I'm just kind of talking about it qualitatively. So it really depends on the temperature of each. You have to be quantified to actually look at very specifically how much time it would take or how much energy per unit time is going in. But just in general, if I started, let's just do it here. So at this point, clearly the slope is higher right here, right? So, but that means, so if I had two different, and this is the same graph, probably should have done a different graph. But if I had two different boiling, this represents two different two different pots of water. If I put in one at a higher, if I start one at a higher temperature and one at a lower temperature, but then, and even if I'm heating them at the same rate of heat, so two different eyes that are at the same temperature, and I can make it perfect. What I was, the hot water will definitely boil first. But if I looked at a change in temperature or a change in time, the cold water would actually take more heat in than the hot water over that range of temperatures because of the way it just, cold water just takes in heat easier when it's colder at a certain, well, once you get it started, right? And so, uh, I'm sorry, it's the opposite. The cold water takes, it's harder to get the heat in initially at the colder the temperature than it is for hot water. So basically, you would have to kind of look where we are on this graph at the rates of the temperature to kind of see that, and then it starts to kind of saturate out again. Like that's not quite the true. If I took like a warmer temperature started here, but then compared to water that's already hot over here. But at some place in there, the thing starts to boil, so it doesn't really show the boiling point here. So it probably wouldn't become water anymore. This would just be the water molecules maybe left in there in the water as the water boils. I don't know. Like it becomes a little bit complicated. So it's not necessarily a 1-to-1 ratio. But that's actually the point. That's actually what they mean when they make a statement like that. It's a more complex statement because it's talking about how the water or the fluid, the liquid is taking in the heat, and that the rate that happens depends on, it's not a constant. Um, it depends on the temperature of the water at a particular time. So I hope that discussion helps a little bit, and I hope that kind of clarifies that statement because just left to itself doesn't really make sense. The first time I heard it, I think I was in in earth science or something back in like seventh grade or whatever. And it just blew my mind a little bit. It didn't make sense. But this is the situation. So specific heat then is the amount of heat. Uh, I think technically you could. It's a specific definition. The amount of heat required to raise 1 gram of one water 1 Celsius degree or something like that. We don't have to get that technical. What I would like you to just know is that that it determines the amount of heat per unit time that one object can take in compared to a different type of substance, one substance versus another. So maybe I should write that down um, since we talked about it. So specific heat. Maybe I could because we're going to define temperature here in a minute. So maybe I should give you the right definition. The more, uh, the amount of heat required to raise, actually, it's 1 kilogram of a substance. I said 1 gram, I think. 1 kilogram of a substance, 1 Celsius degree. Okay. Hopefully you can see that. Oh, it's capitalized. Yeah, and of course, vector magnitude is vector is magnitude and direction. Also, what is heat? Heat is related to energy. Um, yeah, basically they're the same thing. Actually, it's like a different form of energy. You know how the other day we talked about different types of, but mechanical energy, kinetic versus potential. Well, this is just another form of energy which is not considered to be mechanical energy. It's a different category of energy. So heat is energy, straight up. Its units are in joules. And we know that it must be related to other forms of energy because, like work, because like if you take your hands and rub them together, what happens? On a cold day, you kind of rub them together, rubbing yourself, because the friction, which is a mechanical quantity, basically generates heat. The friction of rubbing your hands together generates heat. So where did that heat come from? And this gets into the first law of thermodynamics. It's um, and we can show how it's related to mechanics. Well, heat warms you up as energy, but that energy had to come from someplace. When you're rubbing up your hands like this, where do you think the heat energy comes from? Anybody? And a big hint that if you just put your hands together and you didn't rub them, you wouldn't heat up. So where is that heat energy coming from when you rub your hands together? Delay. You want to give it a guess? Friction. Awesome. Now, how does the friction, well, thank you, Tamiko. How does the friction generate heat? Why? What is happening? And these are mechanical. This is something you should have read in last week. Can you give me a one word quantity that discusses or would describe how the friction is generating heat? What is it doing? Anybody? This might be a little bit of a leap, but what is it doing? What do we call that from a mechanical point of view? What quantity? What physical principle is allowing friction to basically generate heat? Let me help you on that. That might be a stretch. No, the heat and the thermal energy are the same thing. So you could say, but the good job, good try, Kate. You could say that the heat, the friction generates heat, or you could say that the friction generates thermal energy. You can use those two things synonymously. That's what I'm doing here. That's the basic definition that I'm actually giving for heat, that it is energy, but thermal energy, you could just a more descriptive, specific term. So these are really the same thing. So not quite what I'm looking for. Kinetic, well, you're getting there. They're related. Uh, it's that what we say is that the friction does work on your hands. It does work, and that work, because remember last week we defined potential energy, kinetic energy, but you also define work. Well, work is different than, even though it's the same stuff. I said that they're actually somewhat different in the way that they relate mechanically. So kinetic energy is energy of motion, potential energy is energy of position. Work is basically energy that's either taken in, put into a system, or taken out of a system, basically dependent upon how we what we're what we need, and how or what type of work we're doing. So I don't think I wrote that last week. I wrote the definition of work from the equation that we use to calculate it. But I'm going to write this down because this is actually kind of a different way perspective of thinking about work. What I just say was really good. Work, uh, yeah, work can either puts energy into a system, or it takes energy out of a system, or it either transforms energy in a system. It can do all these different things depending on what type of work it is. Work can put energy in a system. Three things. Work can take energy out of a system, and it depends on what type of energy we're talking about out of a system, and also how you define the system. And work can transform energy within a system from different types, say from potential to kinetic. If I have a block on the table and I pick it up, I'm doing work on it and I'm putting potential energy in the system. Like right now, it's on the table, there's no energy, potential energy. I do work on it. Work is force times distance. Now that thing is at a different height and it has potential energy. Well, like we were talking about energy being a ghost, where did that energy come from? It came from me. How? It came from me because I did work on it. Now, if I drop it, gravity can do work on it by taking the energy out of the system again, right? It pulls it down, converts that potential energy into kinetic. Just before it hits the ground, it has transformed, what I was about to say. Work can transform energy within a system. So that last example was when I dropped it, was an example of gravity doing work on the object, transforming the type of energy it had from potential to kinetic just before it hit the ground. Now, when it hit the ground, another thing happened. You heard the sound. Well, sound is energy. That energy had to come from someplace. Where did it come from? It came from the kinetic energy that the object had just before it touched. And also, uh, you could measure, if I would have very sensitive equipment, I could measure the temperature of the podium at the point where it hit, and also the temperature of the object at the point where it hit, where the two surfaces collided, and I could show that the temperatures would change. The temperatures would go up a little bit. Why? Because even just that hitting, you get a little bit of friction there at the point of contact and the temperature. So all of that kinetic energy at the point of contact was converted to sound energy, mostly sound, but also a little bit of heat due to friction. Now, We don't really account for that in mechanics because sound is not mechanical energy. Heat is not mechanical energy. It's a different type. And in that course, when we're looking at that, we're not concerned necessarily about the other types. But overall, none of the energy was destroyed, right? If we were to look at that. Uh, and that gets to the idea of conservation of energy, which is brings us to the first law of thermodynamics, which is a different way of stating conservation of energy. The first law of thermodynamics is conservation of energy for quantities like heat, energy, and thermodynamic properties. I'll get to that in a minute. But just to review here, heat is energy. Work and so three kinds of ways that work can do stuff on a system. Take it out, put it in, transform it within the system, um, and yeah. Um, Sorry, I just lost my train of thought. Wanted to make a point before I left this. Is that sorry? Oh yes, I wanted to make a point about the finish of the point about the friction. So that by rubbing your hands together, um, you are generating heat. But now we know that heat is energy, and that all heat must be conserved. Like when you rub your hands, that heat energy is not just spontaneously being created out of nothing. That would be a violation of technically conservation of energy. So the question I wanted to ask is if I by rubbing my hands together I'm doing work, one hand is doing work on the other, and vice versa. And by doing that work, friction is generating thermal energy or heat. And if heat can't just be spontaneously created, energy, heat, energy, simultaneously using those words, can't just be spontaneously uh, generated out of nothing, where is that heat? Where is the energy coming from that I'm that allows me to do the work? Because it must be coming from someplace if it's not spontaneously generated and it's being converted into heat by the friction. But where is that energy coming from in the first place? Anybody? Geneva? Give it a shot. Stephanie? Soleil? Well, where do you get the energy to rub your hands together? Actually, it's the same source that allows you to walk across the room. Right? It's the biological processes of your body that allows you to contract and expand your muscles in your arm, and it's physiological. Uh, yeah, from your hands moving, and that's your muscles expanding and contracting. And so your muscles are getting energy from you process the food, you get the energy out of the food. So that's where that energy is coming from. It's the energy that you basically from your body, which your body got from food that you processed, and energy from the food. Again, it goes back to this cycle that we kind of mapped out last week. The end that energy goes from plants that you ate, or maybe if you're a meat eater, from the cows. If it was a hamburger, yeah, but the cows got the energy from the plants too, because they just eat plants, right? Grass, whatever. Where did the energy come from in the grass? Well, it came from the photosynthesis of the sun. And where did the energy from the sun come from? Well, it came from when the sun came together and formed this furnace of out in space. And where did that energy come from? Well, it came from some stars a million years before that blew up and sent this gas out on the. So, it's just a cycle. Like all of the energy came from initially how when the universe, well, the going theory, we'll just go with that for now, from the Big Bang, right? Um, it's like never ending energy. And that's correct. That is exactly how it is. It never ends. It's never ending. It's if you look at the grand scheme of things, there's only a certain amount of energy, technically, that, with the given theory, this may not be correct, but it's what we think right now. It started from the Big Bang, right? And whatever, so energies, if it gives you, if that implies that universes can be rated, right? One universe might have more energy than another universe when you get to the multiverse. And yeah, there is something beyond the universe. There's a multiverse of all other. We just think it goes on and on and on. That's the going theory right now. But anyway, I digress. But just thinking about our universe, there was a set amount of energy that's associated with it. And everything that you see, it's just that energy changing forms, just like a ghost, like how I told you. So I think it's important to see that big picture because that actually leads directly into what we describe as the first law of thermodynamics. The first law of thermodynamics is looking at that conservation with a very specific example. Just like when we talked about energy of being conserved between kinetic and potential for an object dropping, that's a very specific kind of zooming in on some specific object and not thinking about the global universe, but it's looking at defining energy in a very specific way and looking at how it's conserved within certain parameters that you set up for a problem, certain given initial values of a problem, a very specific problem. Well, we're about to do the same thing, a very similar thing, with considering the first law of thermodynamics and how heat is transferred from one system to another, which we all have an intuition about because you started doing things like that when you were a kid. You take a glass of water, you take ice, think of room temperature water, take ice, put it in the water. After a certain amount of time, the ice is melted, so it's lost heat, and the temperature of the water is colder, so it refreshes you when you drink it more so than uh, temperate or room temperature water. So the water had to take on energy, right? That is a practical example of the first law of thermodynamics, which I'll read in a minute. But one thing I want to say before I go into that, which I never actually said, but I think we have enough um, enough information generated in this beginning of the discussion to talk about what they're trying to describe in that very first section of the chapter, thing that says nature's direction. Now, before I make this statement, I'm going to give you a caveat. A caveat is something that is uh, it's uh, it's like a idea that you got to be a little bit careful about. And I'm always going to be reminding you of this because it's kind of a big deal for me and for most scientists. But it's a thing where it's just caution. It's just caution. I think as scientists, we should be very cautious. Intellectual arrogance can always seep in and just muck things up really badly for humanity. And so I think as we evolve, hopefully we're evolving and not digressing, uh, not devolving. So as a physics professor, science teacher, I always want to throw this in because this thing, even they put it at the beginning of the chapter, it's quite significant. It's actually much more significant than the idea that they're describing here is much more significant than the time they give it in the chapter. It's a huge principle. And it's something called entropy, is what they're talking about here in this first thing. Entropy. Entrapy. Entropy. Entropy is defined as the amount of disorder of a system. I even said, how do you measure disorder? Well, you measure it through energy and how the energy is compacted, stored in a system. So entropy is the amount. This actually was a tough concept for me to understand. Is the amount of disorder of a system. So it seems so weird, like, okay, like, and when you talk about a system, you could be talking about anything. Like this eraser is a system. It's metal comprised of atoms and molecules in a certain way. Okay, I could go inside and talk about its internal structure as a system, or I can describe it as a system macroscopically relative to its external environment, which is what we do whenever I'm talking about it dropping, you know, in a, a gravitational field near some flat surface. The system in this case would be essentially the Earth, the gravitational field of the Earth, and I'm not really looking at the Earth as I could look at it in two different objects in space, but I'm simplifying it by taking just the flat surface as the Earth and the field that the Earth is creating. But technically speaking, the system is both the Earth and the object. But I can simplify it by just considering the field of the Earth, so it just looks like the system is just this one object, right? And I can look at how it changes. I order it, I put it up some, then I drop it. The falling of the object and the changing of the energy of the object from potential to kinetic, that's what we can talk about in terms of order of that system. So we have to describe what the system is and how we're looking at the system in order to define what we're talking about, what energy we're talking about, and how that order of that energy is changing. So, for example, going back to this, that's one way I could describe the system, as I just did, as a macroscopic system responding to its external environment. But if I were, looking at the specific heat, if I were strapping this up to a really complex experiment and raising its temperature by putting heat into it or exposing it to heat to measure specific heat, now, even though I have the same object, I'm describing the system differently. Now I'm kind of microscopically considering how energy is going into the system. And I know that's going to change maybe the way the atoms in the crystalline structure or the structure of the material is changing. Why is that? Because what does heat energy do? Well, it causes the molecules to vibrate, just like it does when you heat water up on a stove and it turns from liquid to gas. Well, it turns out that solid material, so in the case of water, we call that changing state. And you kind of think of, well, we kind of think of four macroscopic states of matter. When we're just loosely talking or in lay terms, in everyday terms, we say, okay, there's four states of matter. There's solid, liquid, gas, and then plasma, which is what the sun is, stars are. It's slightly different than a gas and behaves very differently. So we call those states, but those are really macroscopic states. It turns out when you look inside material, even if it's solid, as you take, and that's those states that I just described are when you're putting heat into a system externally. Well, what happens if you begin to take energy out of the system such that it starts off as a solid and just gets colder? It turns out that as you go down to lower and lower temperatures, things can rearrange inside the material, even though from the outside it looks like it's not changing. So even though the state of the matter is still solid, matter itself can have different types of energetic states relative to its internal structure. So as you take the energy out and it gets colder, the material can have different behavior. And it's because the way the atoms are being held together, they can dramatically shift to a different state, energy state, even though the material stays solid. That's what we're referring to here when we're talking about entropy. It's how the energy essentially is being ordered in the material based on the way the atoms and molecules are structured together. what we find is that there is a rule in nature. The rule is that it seems like all systems that we can consider, when we look at them over time, like talking millions of years or thousands of years or tens of thousands, whatever, over time, it seems like whatever order, energy state a system has over time, it seems like that energy state somehow dissipates. So we say that in this universe, it seems like all systems seem to disorder as quote unquote time uh, passes. Now, and that's why things decay. Like you put an apple on a stove, or out in the sun someplace, you come back a year later, it's probably decayed and started to decompose. Because the atoms literally, if everything is energy, the atoms, they're decomposing, they're breaking apart, so it's losing the order that it had before you saw it. Now there's some things like even atomic decay, radiation. Like if you have to be careful of certain elements because they radioactively decay, they lose electrons and things like that, and those things move out. And the radiation is just those things are traveling, and they can hit your body. And because they're so small and have such high energy, they can hit like a cell in your DNA and start to change that DNA. That's all radiation is. I don't know if you knew that. Yeah, it's like, we'll talk about the Einstein model here in the next chapter, but not the Bohr model of an atom, but like there's a simple model of an atom that was one of the first models that was described that you probably have heard about: protons and neutrons in the center and electrons around. But more complex atoms, they have more than one proton in that was just a hydrogen atom that I just mentioned. But like a platinum atom or something, there can be a whole bunch of atoms in the nucleus and a whole bunch of electrons and different energy levels and things like that. But there's some elements that are stable, some elements are not. So that electrons and things and basically particles in the nucleus can, for whatever reason, it's unstable, so they can decay, they shoot out. So it's almost like this little very fine particle just moving away. But if it hits your body is just made up of atoms and protons, neutrons too. It can hit those atoms and then affect them because the frequency of the vibration of the wave that the radiation has might be close to the frequency of vibration of the atoms, whatever, in your body. And so it can absorb that. And it absorbs it in such a way that it starts to hurt the atom in your body. And so it can cause that atom to start doing things like decomposing or whatever, or just whatever. And that's what radiation sickness is. That's what will kill you over time. It can do it very, very terribly. And when you see, I don't know if you saw the movie Chernobyl about the big accident that happened in Russia back in the 80s, and you look at these people who were exposed to that radiation just in the wind. It was like a solar wind, right? Like they're standing up looking at that radiation is just like being close to the sun or something like that. And so many of them got radiation sickness and died within a couple of days. And some of these people who initially went in there, they were like, they just walk over there because they didn't know what happened. They're walking toward Chernobyl, and like in 20 minutes, they fall on the ground, and 20 minutes later they're decomposing. It was that bad. And they've just, I think they've encapsulated that whole area with just a big concrete dome or something like that. I don't know how they did it, but whatever, just to try to keep that stuff contained so it doesn't get out and you know travel throughout the wind, travel and hurt people. Anyway, I digress. But the point is that entropy is about the order of a system, and ultimately, when we're talking about order, we're talking about how the energy is stored in a system. And that is related to many things, but it's basically how the electrons, the atoms are stored in such a way that's ordered. It's kind of like right now the books on my shelf are ordered, right? But over time, what you would see, and this would probably take tens of thousands of years, but over time, the wood is going to decay. The books are going to decay. They're going to decay. You might touch them. You're like 3,000 years from now, you come up and you hit it, and everything just turns to a puff of dust, right? Because the strength of the atoms holding themselves together, or they're losing that energy, and so things are just decays. And everything does that over time. And one way that we can measure one quantity that we've figured out how to measure that decay. Well, I'm saying decay. That's just one example. It doesn't have to necessarily be decay. It's just disordering. That's the technical term. That this quantity entropy measures that, and this is what they're talking about in terms of nature. That whole section there is really, I don't think they use the term entropy because it's a more advanced term, but that's really what they're describing. Question: when the books decay, does it lose molecules? Uh, yeah, I guess you could say that. Lose, you'd have to define what that means. The molecules uh will basically come apart. That's right. Yeah. Because you think about water. Water is H2O, right? It's a molecule that looks something like this. You have one big oxygen, and then you got these two hydrogen atoms. This is oxygen, this is hydrogen. And it's a molecule. It looks like an anvil, if you could see it. And it literally looks like that. And it actually vibrates. Water has a certain frequency of vibration. So, like, if my the oxygen molecule is down here with my elbows, and I can attach them somehow, and that my fists are the hydrogen molecules. It actually has a natural vibration, just like it would if it were a mechanical system that I could make. You can imagine that natural vibration. Well, what happens if I can put energy into that? Well, the thing starts to vibrate more and more. That's what happens when you boil up water. Actually, a better example is the microwave. Does anyone know how a microwave works? How it heats up food? Anybody? No? Caitlin, do you know? Because this is really fits your question very well. Let me tell you. Very ingenious thing. It's one way we've used to exploit uh, a physical phenomenon for our practical purposes. As you know, most things have water in them. In fact, our bodies are, I don't know what the percentage is, something 70% water, 80, I don't know what it is. Someone might know. I'm not a biologist. I don't have that stuff memorized, but we're mostly water. Well, like our tissue, muscles and stuff, like meat, whatever, even food, plants, vegetables, they have water too. So it turns out that water can absorb electromagnetic radiation, right? Like heat, like this light is heat. If you put your hand close to it, the skin can absorb some of that radiation and it warms up your hand. Well, it turns out that I think it's ultraviolet B. No, not ultraviolet. It's uh, yeah. Which wave is a micro? Oh, a microwave. Duh, microwave. So it's just light with a certain frequency and vibration, and the energy is vibrating and it travels on a wave. Let's just leave it at that for the time being. And most things in nature, in order to even see something else, they have to have frequencies that are within the same range. Um, but again, that's a symmetry and a pattern that doesn't just necessarily respond to light. It kind of, everything kind of abides by that. For example, when you were a kid, you maybe played on swings. Well, swing frequency and period. Frequency is the amount of oscillations per unit time. Period is the time per oscillation. But the point is, it's some sort of uh, oscillatory thing, some motion that's happening over and over again. All right. So we can relate that swinging to the fact that if you look at a water molecule and it's vibrating, it's also doing something over and over again. It's motion, it's oscillatory motion. It's a specific type of motion where the object basically vibrates. You can vibrate, you can spin, turn, rotate. In this case, we're talking about vibratory motion, but that's a specific kind of motion in nature that we study. And so when you're swinging on a swing, it's called a periodic motion or a pendulum. It's similar to that kind of vibratory motion. Okay. Well, if you're on the swing and you want to, you're trying to get yourself to go higher, you want to go higher, but you can't. You've reached all the effort that you can to make yourself go higher by kind of, pushing off the ground, whatever. So you beg your mom and your dad to come over and uh, make you swing higher. Well, what do? Well, they have to drive you. They have to give a driving force where they push you. But they push you in a very specific way that's intuitive to everyone who's done this. You probably don't have to be a physicist to know this or a scientist. You just kind of do it naturally. Whenever the person is going down, you push down. And again, which means that at every point, you're matching the frequency of that swing, right? Push down, you go down. And what happens? The energy of the push, you do work on the object basically, and that energy goes into the system and the amplitude increases. So essentially, you can think of your push as an external driving force, which matches the frequency of the swing. Because they match, the frequencies match, they see one another, and the energy can be absorbed, and the person goes higher. The exact same thing is happening with a microwave oven and the water in the food. It just so happens that a microwave, which is a wave, has a frequency that's very similar to the natural frequency vibration of water. So it's vibrating, minding its own business. This wave comes in. They have a very similar frequency, so the water molecule can see the microwave, and because they see one another, they can interact, and the water molecule can absorb the energy of the microwave in a analogous way to how uh, you can absorb the energy of your parent pushing you on a swing when you're a kid, and the amplitude of the energy gets higher. And in the case of the microwave, the amplitude gets higher, and it basically just raises its temperature. And because it raises its temperature, it then can conduct through a different process. It basically conducts that temperature, that heat, to the water, the other fibers of the meat or whatever that's in, and then conducts that heat throughout the material that's being heated up, whether it's meat or plant or whatever it is. So that's how a microwave works, and that's also why the stuff that you're heating up dries out, because if you heat it up too much, because it's heating up the water, and then the water is indirectly heating the the food. But then the water molecule, it might get to the point where it actually disintegrates, it breaks apart, and then it turns into steam or what gas, and it leaves the food. So that's an example where I wouldn't really call that decay, but that's an example of how a molecule can basically come apart. So the process of decay is different. It's associated with entropy and different things. It's not necessarily taking in energy, but it's losing its energy because the water molecule still lost it. You could think of that kind of as a decay, right? It did lose the energy. It came apart. So certainly the energy associated with that was dissipated through heat to the food. But that still over time, the water molecule, its order, it became less ordered or it became disordered in that process. So there's all different types of external processes that can cause things to disorder. But the point about entropy and the point about the universe is that all systems over time, no matter what, we think that the property of our universe, that all systems, whatever order they have at any particular given time that you observe them, at a later time, and you have to kind of look at maybe in terms of the universe, large expanses of time. Over time, the system will become less ordered or more disordered. And entropy is a measure of the disorder. And also, I want to put this in with there are certain quantities in physics that we define in the negative, which is always a little bit harder to kind of maybe understand them. Entropy is one of those. We define it in the negative, meaning it's the amount of disorder, not the amount of order. So you have to kind of put that, what I call that minus sign in there when you're considering it and thinking about it qualitatively. Um, yeah, yeah. So that's entropy, that's disorder, that's what they're talking about there. That we, you know, yeah, things seem to naturally disorder. And the caveat that I was going to talking about, that I mentioned in the beginning, is uh, I think we just have to be careful. Like we call that kind of a universal law, whatever, a big law, and it may be true. I'm not saying it is true, But I think you just have to be careful because I have a feeling, a gut feeling that this idea of entropy, it may just be a reflection of a larger principle in a higher dimension. But it's the way that that principle is kind of manifesting itself in our three-dimensional space-time reality. I know that sounds really quirky and it's kind of getting, but some reason I just think we have to be careful. And again, it goes back to that analogy I was making last week, where in the three-dimensional space-time, this is my hand, but for two-dimensional people living in this wall, they don't even see that. They don't even see the shape of the shadow. They only see a line. Like if they're two-dimensional, they're looking down that shadow, it's just a line, literally just one dark line. That as I do this, that line gets shorter and larger. So when we talk about entropy and the disorder of the universe, like I think it may be, it just I don't know. I don't know why I feel that way. It's just some things, some principles that we kind of discuss and we're trying to figure out. In this case, when we think we know, I think it just may be a little bit more complicated than that. But it's just the way it manifests in our three-dimensional space-time reality. It just, I don't know. I don't know why I feel that way. I have no other proof other than my intuition. But there's certain concepts that we know about that we study. It just hits me that way. And I feel like this is one of those. But this is what it is. This is what we know and this is what we teach. And certainly we've worked it out to at least in our space-time reality, these things work. These equations that we have to define them, they work out. A couple other things that came up I thought about. So the idea of this thing changing state, even though it's staying solid, there's some very famous examples of that, and one is the concept of superconductivity. Does anyone know what superconductivity is? Well, it's where there's a certain quantity that we'll talk about in subsequent chapters called resistance. When you're looking at circuits and electrostatics, you create a circuit, electrical resistance. It's the reason why you have to keep buying power from your power company, right? Every month, they have to keep generating it because when you put electrical power in something, basically it's friction. It's friction. We'll talk about it later, but basically how the current that you're buying, it's basically charged particles moving through a wire, but they hit other stuff. It's why your eye heats up. We use that positively when you have a conventional stove and you turn on your own electricity and it heats up. That's using electrical resistance positively because it makes the eye really hot and you can use the heat. But when you're talking about your computer and your computer heats up because of the electrical circuits and current running in it, that can actually hurt the system. So we have to have a fan to keep it cool. So that's one case where electrical resistance is not so good because it can damage things. Anyway, it turns out for certain types of material, they become what we call superconductive, meaning at certain temperatures, the thing that causes resistance in those materials completely disappears. And that's because the energy state, the molecular and atomic state of the material drastically changes. Even though on the outside, it still looks like it's the same material, on the inside, it's not. And it's one of those properties where, and there's all kinds of exotic things can happen, and this is one of those exotic things that's very popular, that the resistance disappears. So if you put electrical current in the thing, it doesn't dissipate because there's no heat energy, there's no friction, the molecules, there's no resistance there. So the electrons that are moving that cause the current, they're not hitting anything to lose energy. So it doesn't get hot and the current stays in there forever. Yeah. So you could, for something that is a light bulb, for example, that is a superconductive light bulb, once you turn the switch, wouldn't be accessing energy from your wall, from the company. It would be, the current would be in there in some circuit somewhere, and you could just access the current that's inside the device, and that current would turn the light on, and you would never need a battery or anything. if it were superconductive because the energy would never dissipate that's in the current of the system. Now, so if everything that we had were superconductive, you wouldn't need a power company. Well, at least not as much as we do now, because once you put the energy, the electrical energy in the system, it would never dissipate when you use it and access it as current. The problem is that objects only become superconducting at very, very cold temperatures. So it takes more, just as much energy or more energy to make it superconducting and keep it at that as it would to, that it to maybe more energy than to just have a regular material and use it not use a make a non superconducting device out of that material. So that's a whole area of physics where we're trying to find and create materials that become superconducting at room temperatures, and we don't have to keep them cold. If we could do that, it would drastically. You think that technology is going fast now in the past? Well, in your most of you probably are 20-year-olds, but I'm 60, so I certainly have a little bit more experience, life experience. So I remember when we didn't have cell phones and things like that. It was basically all throughout my childhood and into my early 20s. Um, so things have very much in technology has, as you know, has increased. You've heard that probably, but maybe have a slightly different perspective than I do. For you, it's like the difference in the model of the cell phone. For me, it's like going from, you know, back in the, you know, late 60s, early 70s to dial, analog digital phone to digital, which is crazy. But anyway, I digress. But if we could create room temperature superconductors, oh my gosh, I don't know. I can't even describe. I can't even use words to describe just how fast we would, if we didn't kill ourselves first, but how fast we would. It would make what we've done in the past 40 years, in terms of our evolution technologically, it would make that look like, you know, a tortoise versus a hare. It would be insane. I can't even imagine it. That's just one change. There's other things that could make that happen as well, but that's one. That's one. If we could get room temperature superconductors, any of these space science sci-fi movies that you can think of, you know, where it's showing us 100 or 200 years in the future, we could do that in like 50 years, probably less. Yeah, it would be that significant. So, but we do use them now. There are certain things where we use superconductors where it is cost effective to have the material being superconductive and to create uh, devices that we can use. One of them, probably the best example, is the famous bullet train in China, and also the thing that the train that I think is Elon is it Elon Musk that's trying to make a train from California up to San Francisco or someplace like that. That's Elon Musk, right? I think that's either him or maybe Bezos. It might be Bezos. I can't remember. One of those two talking about making that train. Well, it's a train that would be using this technology. The reason that the bullet train is so fast is because the train floats on the tracks. It doesn't you have wheels or I don't know how I don't know the engineering, but basically it floats. And the reason it floats is because the train the rails are magnetic, and the underneath the train is also magnetic. So they have different polarities, and it's so strong that it lifts the train up. And so when the train moves, it's basically floating, essentially. That's why it's so fast, and it is not creating friction because and slowing the train down. Well, what does that have to do with superconductivity? Well, because I don't know how if you know how a magnet is created, but anytime a charged particle moves, and that can be either translating, rotating, or even vibrating. Anytime that happens, that's how a magnetism is created. It creates a magnetic field. And yeah, yeah. And that's how bar magnets are created. For example, this thing has atoms that we talked about, has atoms and molecular structure like this thing. But it turns out that for molecules, I just looked it up. It is indeed by Elon and his new Tesla project. Yeah. Okay. So Elon Musk is doing it. Yeah, wants to do it. Well, electrons spin and protons spin, charged particles, and they have their own magnetic fields. And if you could see it, it would look kind of like the magnetic field of the Earth. This is probably going to be talked about at some point in the chapter or something in the chapter. I'll hit it now a little bit. And you see, I'm not going to draw it now because I'm kind of digressing and I want to kind of move on. But you see what the magnetic field of the Earth looks like. Well, the magnetic field of an electron looks actually very similar, and a proton. They spin and they have and they're very small, but they're everywhere. Like they're because everything is made of atoms. But the reason that most things aren't magnetic is because the poles of the atoms are all like dispersed in different directions, so they cancel themselves out. That's why I'm not magnetic and you're not magnetic, because our electrons, the individual magnetic poles or magnetic moments is what we call them, physical term. They cancel one another out because they're in random directions. But the way you make a bar magnet, and you can do that either naturally in the earth, because the earth has a magnetic field. So if something was liquid magma or whatever, and it's forming into a solid and it's forming molecules and it's protons and electrons, if it's exposed to a very strong magnetic field, which it could be down inside the earth, then as it forms, the electrons and protons of the solidifying magma, they shift slightly so that they don't quite cancel out. And then when it hardens like that, so that the object is now magnetic. And that's actually why you can make a magnet, right? If you have a very strong magnet and you take a paper clip, which is non magnetic, and you put it on a magnet, the external magnetic field of that magnet, because even though this is solid, because remember, I told you, like the water molecule, the molecules are moving. It may not look like the atoms and molecules inside this metal, this steel is moving, but they are. They're vibrating and they can shift around, even though they don't translate and you can't necessarily, the magnet is not strong enough to break the material apart. The atoms, they feel the magnetic moment, that they feel the external magnetic field of the bar magnet. If it's very large, very high field, and you're very close to, you take the paper clip and place it very close to the magnet. So what happens is those protons and electrons, they kind of act like compass needles because they're vibrating, they have their own thing, but then they see the external magnetic field and they can slightly shift just a little bit. And there's a whole lot of electrons and protons in this thing. So all of them only need to shift just ever so slightly, so that now the magnetic field, the individual magnetic field aren't canceling out, and you get an overall magnetic field of the paperclip. So now it's slightly magnetic, and you can put it on something and attract other paperclips for a certain amount of time. But then after a while, they're still vibrating in their atomic sites. After a while, that vibrational kinetic energy takes over and causes them to kind of go back to their normal positions, and then they're now completely random again, and they're not magnetic. So I know you've experienced that as a kid, and that is one physical explanation as to how that happens. That's why you can magnetize something. You can even magnetize a person. In fact, they've done it. They've magnetized very small frogs, and you can place a frog and cause it to become magnetic. Now, I don't know what that does to it. Probably messes up the frog or whatever, but they've done that before. And I think they did it in France back in the 80s. Yeah. Yeah. So, I don't know how I got on that tangent, but uh, yeah. So you can magnetize things, and that's where magnetism comes from. And oh yeah, I was talking about the bullet train. So the bullet train is that. So that's how magnetism is created: is by either translating, vibrating, or oscillating oscillating, rotating charges. Well, in the case of the bullet train, it's translating. You take a current and you put it in the tracks. It creates a magnetic field. You do something similar in the in the whatever the mechanism that's under the train that holds it or keeps it on the track, and you make them different polarities, and it lifts the train off the track, and so that when the train moves, it's actually floating on the track, and so you have much less friction. Now the thing is, it takes a lot of energy because the tracks have to be cold because they have to be. So with super, oh yeah, so with superconducting, you can put a whole lot of current in the thing because it doesn't have any resistance, and you can create very large magnetic fields. That's why you can lift something like a train filled with people off, because the magnetic fields are incredibly high, because the current can be incredibly high. Why? Because the metal is superconductive, and it's not generating heat as you put this high current through it. And so it's cost effective to do that. Why? Because the train generates a lot of money. Because like in China, there's a whole lot of people in China. China's a big place, a lot of land mass. So you're going up to southern China. So it's work. Like you got a lot of work people. So it's generating a lot of money. So that's why it's cost effective to be able to maintain something like that, because it generates gobs and gobs of money because so many people use it. Same, that's why Elon Musk is you wouldn't do that at certain places in the country. You wouldn't just make it. You got to make it where there's a lot of people, there's a lot of workforce transit. You need a cheap way to get it back and forth, cheap, very quick, because that also generates money for the economy, right? Because people can now access work very much easier, and you can carry a lot of people with the same device. So that's why it makes sense to consider something like that. And they're going to do it. I mean, they're going to do it at some point, because it just technology is such that we're there now where we can do things like that, and yeah, so that's going to happen probably at some point pretty soon in the next 15 years. So that's one use of superconductivity, and that's an example where something changes its state, although on the outside it looks different. It's superconducting metal is completely different, in terms of its electrical, obviously, because of how we can exploit it. Its electrical properties, its thermal properties, all kinds of properties change because of that transition, that superconductive transition, phase change, essentially, energetic phase change, not macroscopic phase change. Okay, so that's a lot of information that's maybe somewhat extraneous, but kind of gives you context, which I think is extremely important in understanding concept. Okay. Oh, they do talk about specific heat. They give it one little chapter. Okay, they don't give the S curve. That's in there. So I'm kind of the way I'm discussing this is a little bit more organic. It's not necessarily the order in which the chapter is discussing it, but we're pretty much almost finished with this chapter. One thing I want to kind of going over the break a few minutes, but now that I got you here, I want to do a couple sections real quick: heat and temperature, and then conduction. Tell you because we're almost. I just have to maybe just 5 minutes to kind of give you an idea of what to describe what conduction is and how heat is actually transferred. There's a couple of different ways. Conduction is the main one, and they have conduction and convection that they talk about there. But just again, in general, going back to how what temperature is and how temperature relates to heat. So temperature is a measure of heat, but what are we actually measuring? I think this last discussion that I had about magnetism is really nice. How we're magnetizing a paperclip, because I gave you the idea of vibrational kinetic energy. Well, uh, it's always good. I'm a visual learner, so anytime I can have a a picture, like I gave you the picture for a specific heat, as opposed to just giving you the definition, right? You're not going to find that picture in your book. Uh, because that's just how I learn. I have a pretty vivid imagination, and so I use that imagination to construct almost like visual laboratories in my mind so that I can see things. It's what models do in physics when we have these various models. So I'm going to introduce something that was first introduced by Einstein, which is a little bit different than how they have a model there, but it's a little different. It's going to be called I'm going to call this the atomic lattice. Now, this is not there's several ways that you can describe matter. Over here I described a molecule. Well, this is looking at it slightly different, not looking at something comprised as the molecules in an object, but rather how the atoms come together to form, or essentially it would be how the molecules come together. But when Einstein first did it, he didn't really describe it in terms of molecules. He just said that the most basic model of matter, and this could be any kind of matter, your hair, a fingernail, that paper clip. If I could look down and go inside, get on the level of like Dr. Seuss character, like Whoville or whatever, they had like a world on the head of a pin. People that small, where I can see the atomic structure of the material, whether it's wood or glass or whatever. Einstein first proposed that matter is made of very, very small corpuscles of matter, which we now call nuclei or protons or whatever. So, very small atoms. And they're connected by, you could say that, and now he knew there were no small springs down in the thing, but he could say for all practical purposes, these atoms are connected by what you could refer to as springs. They're all connected. And it's kind of like slinkies, like if you took balls and then you put slinkies and you connected a bunch of balls together and glued the slinkies to them. Any kind of matter that you could think of, like I said, your hair follicle, a fingernail, anything, that would be a basic model of the thing. Atoms combined by very small springs, and this is called an atomic lattice. This was first proposed by, I told you, Einstein was very smart. Most people only know him for a few things, but this was the first thing, this was actually the thing that made him popular when he was really, really young, years before relativity came across the picture, at least 10 years or so. So this is attributed to Albert Einstein. Uh, so it's helpful to have this as a picture in your mind when you're thinking about stuff heating up and about energy transfer. And because all heat is, or how it manifests in water or in whatever, is these atoms, they naturally vibrate. They naturally vibrate. In fact, the only way that they would not be vibrating is if somehow you could take all of the energy out of them, all of it. Now we think of that. You take something and put it in a bucket of liquid hydrogen or liquid nitrogen, it freezes real quickly. Or we see these space age movies where somebody's out in space and then somehow their uniform gets broken and then they go out and they freeze and they're floating out frozen. Even in that case, all of the energy has not been taken out of it. There's still some energy, if you were to there's still some kind of vibration if you could look at the molecules. Even though they look like they're frozen stiff, they're not down to 0 degrees. In fact, we think it's theoretically impossible to take all the energy out of something. That's a different story. But the point is that for all of us in normal, room temperature, if you looked at our molecules and our atoms, they would be vigorous vibration on that level. Everything is vibrating. Okay? Now, what heat is, how it translates, is when you put energy where there's thermal energy, electromagnetic energy, even like rubbing, like just like say this edge here, this is what my hand looks like if I could go down an atomic scale. So one hand, this is the edge of the hand, and I could put another lattice on the other side that represents my other hand. And when I'm rubbing them together, basically it's friction, right? It's just like this atom is rubbing against something else. And so that rubbing causes, as we said, one is doing work on the other and it heats up. But how does that heat manifest in this lattice? Well, it causes the atoms that are on the edge to vibrate more. Right? You know that. You can see that kind of think about that when you're boiling water. Or let's just say that I put all of you. Let's do a thought experiment where we make a lattice. I take, basically what 20 of you, and I put you in a small classroom, and I kind of set you up in a square, kind of like this, 5 people in a row, 4 rows, and then I give you a slinky, and you're holding the slinky, right? Well, you kind of fidget. Maybe after a while, you kind of move around a little bit, right? You're moving around, you're fidgeting, whatever, and the slinkies are moving. But what if I then put you in a small room and I start to turn up the temperature? 70 degrees, 80 degrees, 90 degrees, 110 degrees. But I tell you that you have to stay in that spot and you have to hold the slinky. What are you going to do? Well, you're going to start to move around even more, maybe wiping sweat, it's more vibration, right? That's literally what happens when you heat up water. That's from the Einstein model. That's why it was such a brilliant model. In fact, I think he actually got the Nobel Prize for this. He didn't get the Nobel Prize for relativity, or actually, maybe that's wrong. It was a couple things he did. I have to look that up. The photoelectric effect, but it was one of the basic things that he actually got the Nobel Prize for. It wasn't one of these things that we know him from, and I think it might have been this. I forget. It was either the photoelectric effect, which is something completely different, or it was the Einstein model of a solid. I can't. But this was huge because he did this around like 1903 or something like that. You would think that we would already have, like, this is the first time that someone actually made a stab at trying to figure out how matter is put together. You would think that it would have happened years before that, but no, it's the first. It's the first model that we had. Uh, he might have done it. It might have been before. It might have been like around the 1890s, but relativity, I don't think he proposed until 1908 or something like that. Um, and then he got the Nobel in 1915, but it was from one of the earlier things. I think it might have been the photoelectric effect. But this is the thing that made him famous, actually, his model of a solid. Anyway, because it's brilliant, right? Because like we take it for granted now, I can come up with this thought experiment and give it to you, like and tell you, and you're in a room, and you could very much feel the reason it's brilliant is because it just makes so much sense, right? I just describe this kind of model of you with slinkies in a room, but who in their right, like who is going to think that a piece of plastic is that also applies to that? Nobody. It's brilliant, right? Like you just, he was just able to visualize these things in ways that people weren't. Like he said, he came up with. I think I told you this. He came up with relativity by imagining himself surfing on a light beam in space. Okay, well, when you and I kind of think of a space on a, like, okay, I'm surfing on a light beam. But with Einstein, he had his right brain was so advanced that basically, I guess in his mind, he could think so well that it created like a holodeck in his mind. He was literally doing it. I don't know. I don't know how you come up with stuff like that. But the same thing applies when he's looking at a piece of metal, right? He's putting himself on the inside of the thing and looking around at what does it look like. That's how he came up with stuff like this, right? And it turns out it worked because it can describe the vibrational energy of the molecules on the outside. So look, this is how the heat is transferred. You heat them up on the outside, but now they're vibrating more because they're getting either something is doing work on them or they're absorbing electromagnetic energy. Like if it were water, and if these were water atoms of water in the food, whatever, it's somehow on the edge. You're interacting with an external environment that's causing you to take in heat, but that manifests heat manifests by a larger, more kinetic energy. So because they're vibrating more and because they're connected through the springs to the other uh, atomic particles deeper inside the material, then they translate that kinetic energy via the springs that are connecting them. And then the second row starts to oscillate a little bit more. Excuse me, I need to go with some tea. And we should probably take a break right now anyway. Vibrating more the second row vibrates more as a result of its interaction through the springs to the first row, which got its heat energy from being exposed to some sort of driving force or mechanism outside of the material that's causing the heat to go up. So the point is that the way that you can determine whether something is taking in heat energy or expelling heat energy is by the kinetic energy, the vibrational kinetic energy of the atomic lattice. And so what we are actually measuring when we look at the temperature of something, it's how much heat is absorbing. But what are we actually measuring physically? We are literally measuring the vibrational kinetic energy of the atoms or the molecules or whatever it is however you want to break the thing apart. So that is what temperature is. It is essentially a measure of the internal kinetic energy of the atoms and the molecules. Very esoteric things, because again, temperature is another scalar quantity. It's not a vector. Vibrational energy, that's not a vector. It's a scalar quantity. So, and so that's it. That's what, and so they describe that here. I think they have like some molecules in a spoon. And, I that's one basic is a different way of describing what I did here. And I think they have red and blue. You see, the red ones are the ones that are getting more energy, and ultimately they're going to translate that energy to the blue ones. But I love Einstein's model. This is perfect. I mean, this is a very complex thing, but it's brilliant because you don't have to deal with the complexity to use it and explain it in a class like this that's more kind of a conceptual class, is not mathematical. In fact, Einstein said that. He said that if you can't explain something, no matter how complex it is, to someone who has no idea, that's not a scientist, has no idea what that thing is, then that means that you don't understand it very well. And I agree with that. Because with this model, you could use it to explain basically very basic and simple kinds of physical phenomena, or at least explain them in a way that is understandable, or it also suffices for to as a basis for understanding and explaining much more complex phenomena that occurs with the transfer of energy uh, in an object, and also the phase changes that we talked about. So yeah, Einstein was the man. Uh, quite quite awesome. Dude. So let's take a break right now. We'll come back. I'll finish this topic up with temperature and talking about the transfer of heat, and then we'll move on to either the next chapter. There's probably a couple of things I need to say in this chapter, and then we'll move on to. What time is it? I actually need to get I need to make some tea. So that's mm, almost 2 o'clock. What's that? Let's come back at 10:15.
Okay.
That gives us a little bit. Yeah. So I just recap real quick. So with this atomic model here, atomic lattice. So for some reason, you might have energy uh, incident on the material from this side, and it could be whether it's like a light or electromagnetic wave or even friction or something is causing the kinetic energy of the molecules on the side here to increase. That's what happens when heat absorbs heat, whether by work or by absorption of a wave or electromagnetic wave or light. And they just start to vibrate more, and so they translate that vibrational motion through the springs to the other ones, and it just kind of moves through like a small wave, and that's how heat flows. That's what conduction is actually. So they define conduction a little later on in the chapter, but that's how that's what conduction is. It's a translation of the kinetic energy of energy through the vibrational kinetic energy of the molecule. Now, the absorption is a different process, whether it's the work done like by rubbing or whether it's light incident. That can be a different process other than conduction. But conduction is the translation via the vibrational kinetic energy of the molecule. So that's what they're talking about there with heat transfer. Yes, they have the three different types: conduction, convection, and radiation. Um, uh, and they define convection here as the transfer of heat. Uh, so heat has been transferred from water at the bottom of the pot to the top. Convection, transfer of heat by bulk motion of water itself. And they don't really get, yeah. So we'll talk about that. Let's talk about the difference between conduction and convection. I guess I should write the definition. I didn't. I described it there, but let's give a specific definition for conduction, then we'll go to convection. Conduction works through the action of individual atoms or molecules that are linked together by chemical bonds. Now, the Einstein was again brilliant. These springs represented the chemical bonds, and there's other kinds of bonds too. There's electrical bonds, chemical bonds, but that's what these springs were kind of like mechanical analogies of the chemical bonds. But again, transfer, I said through the springs, they say through the chemical bonds. These are just enough. I mean, there's no springs inside your hair holding your atoms together. But again, it was a brilliant model because it was the first model, and then ultimately it worked in a lot of these things like chemical bonds. I'm not sure that they actually knew the nature of chemical bonds in the way we know them now in 1905. That came a little bit later, but it still fit the model that Einstein had come up with. So conduction. I said it a little bit differently. I came up with my kind of own definition. I said the transfer of heat through vibrational kinetic energy of the atom, something like that. Or just transfer of individual atoms connected um, via chemical and molecular bonds. Well, I'm going to say atomic bonds. I'm going to use a stay with the physics kind of point of view. Atomic bonds. You could describe that chemically, molecularly, or physically. I'm choosing to do it physically. Convection is more of a think of this as zooming out. Well, zooming out from the atomic view to the kind of molecular view, if you will. Um, We know that when we think of a gas or fluid, some sort of fluid, as the temperature of the air in a room changes, for example, near a window air conditioner, it's colder. There's airflow in the room. So this is really a gas. Air is a gas. And as pressure and temperature, as temperature changes, air pressure of the room changes. So you're going to have high and low pressure. Well, you know that something that has a high pressure wants to kind of flow into a lower pressure. You see that on the news when we look at the weatherman every night. Well, high pressure is going to happen whenever something is hotter, as I just told you. This is a solid, but if it were a gas, I could have a very similar picture. It wouldn't be bonds, but I mean springs. But the bonds are looser. I guess it's not really bonds. Yeah, it's just individual molecules. But you could have molecules in a room that basically they're not connected, right? They're not connected in the way that a solid is. But there's a certain volume of molecules in a room, and you can increase the pressure by increasing the temperature. Why? Because the molecules, as I told you, they take on energy, and they have more vibrational kinetic energy. Now, if they're not together, it's harder to see that they're vibrating. They wouldn't be vibrating, but they would be moving around and bouncing off of one another. And the more you increase that energy, heat it up, the more that happens. You can see that with a balloon, for example. You take a balloon, there's a certain amount of air in it, you put it near a hot light, and it starts to get hot and it starts to expand. Why? Because basically the molecules are taking on energy. Again, like, water molecules are floating around in air, they're vibrating. They can take on energy, be heat up and vibrate more. Just like we talked about with the microwave, now that they take on the energy slightly different than they would from the microwave. But you know, in the similar fashion that I described here with a solid, a gas can take on the molecules of molecules within a gas can take on energy as well, and they're going to become more uh, basically translational kinetic energy. In that case, hitting one another, and the more activity you get, uh, it can cause the pressure to go up in the room in the balloon, and that causes it to expand. If I take the balloon and put it in a refrigerator, the molecules become less energetic, they slow down, less collisions, then it collapses. And the same amount of air is in the balloon. We haven't changed the number of moles or molecules, or they're related, moles and molecules in the balloon. It's the same number of air molecules in the balloon, but it expands and contracts depending on the energy of those molecules and how much translational vibrational energy they have and how much collisions per unit time that they're making. Um, so the point is that even if you don't have the air in the balloon, that's what happens in a storm. That's what they're talking about when they have these they show these flow lines of air pressure in